The final reaction we'll talk about today will be polymerization of alkenes. Polymerization is a reaction that is mechanistically quite similar to the reaction we've seen so far, but in terms of its reaction product it's completely different. It gives us a polymer, huge molecule which is composed of a large number of repeating units derived from alkenes. In terms of synthetic usefulness, this reaction is hugely important. Most of the plastics that we use today are polymers, and many of them are produced by polymerization of alkenes. Alkene, this repeating unit, will be called a monomer in such a case. And stitching together a large number of monomers gives us a polymer. One thing that is different with the difference between polymers and the molecules we've encountered so far is that the polymers oftentimes are not, the sample of a polymer is not composed of the same molecules. It's composed of distribution of molecular weights of polymers which behaves in a certain way. We'll talk about polymerization only briefly, even though it's a hugely important topic, in the context of reactivity of alkenes. I'll explain what polymerization is in an example of styrene, which is an alkene. We can also abbreviate this. And if we expose this to an acid, in the absence of any other reagents, what we'll get is a cation, and this will be this secondary cation, which is more stable one. Now, if we don't have any other reagents, then the only nucleophile we have is another molecule of styrene, which will attack this cation, giving us a different cation. And again, it will attack it in orientation, which gives us the most stable intermediate, as predicted by Markovnikov. Now, this can be attacked by another molecule of styrene to continue the chain. And this reaction keeps going until we end up with a very large chain with a huge number of repeating units and a cation at the end. This cation now undergoes things that a lot of cations can do, and that is elimination, to finally terminate the chain and produce something that looks like this. And this will be a cationic, cation-initiated polymerization. So you see that mechanistically this is almost exactly the same as all other electrophilic conditions of alkenes, but the product we get is quite unusual. Polymerizations can also be initiated by radicals. And while in this case we get products which are very much similar, we again get polystyrene. Just label this as styrene. We get polystyrene, we get it to a completely different mechanism. So if we have, again, styrene and we initiate this with some peroxide, then we'll get a radical. And this radical can react with another molecule of styrene to give us a growing chain, which will look like this, which will then keep reacting with additional styrene molecules until eventually we get a polymer which has a very large number of repeating units and a radical at its end. And this can now undergo radical recombination, the same way we've seen in termination of say, radical fluorination, to give us polystyrene molecule. The textbook also gives an example of anion-initiated polymerization, which occurs through, again, anion different mechanism, and again, it gives us the same molecule of polystyrene. But the common feature of all these is that polymerization is initiated by some sort of a reagent, which can cause it to be cationic, anionic, or radical, and it proceeds because there are no competing nucleophiles. It proceeds with the alkene itself. Okay? I think at this point we will finish this study of polymerization, and this will also be the last reaction we'll discuss when we talk about alkenes. But what I hope to aspire from this in previous lectures is that alkenes are hugely important compounds, and that unlike alkenes, they're very reactive, and that the main reaction is electrophilic addition with a wide variety of reagents which then is an entry into a wide variety of compounds. And in our next lecture, we will start talking about alkynes, which is molecules which contain carbon-carbon triplet. Thank you.